Hi everyone, welcome to the second lesson on heat transfer. I know the first one was a bit of a beast because we had to consolidate a few different topics, like we had to revise what temperature was and how it worked. This one is a much leaner, meaner animal. We're going to look at one key concept and then try a few example questions on it. So it should be a lot easier It should be a lot more straightforward. We just got one job to do. So let's start by asking a fairly obvious question. What happens to the temperature of an object as you heat it up? So as you apply heat to something, its temperature should increase, right? Because the particles are moving more, and temperature is a measurement of how much those particles are moving. Now, broadly speaking, you're correct. Usually when you heat something, its temperature will go up, except sometimes it doesn't. There's a couple of particular cases where you can apply heat to an object and its temperature does not go up. Now, to understand why, let's just remind ourselves about the states of matter that matter can exist in. We're not going to talk about plasma and the leaving cert. So you've got a solid, a liquid, and a gas. So if you imagine we start with a solid, to turn it into a liquid, you have to give it heat. The process is called melting, and even though you associate it with ice cubes, any solid can melt if you apply enough heat. The amount will just vary depending on the material. So if you give a solid heat, enough heat, eventually it will melt to form a liquid. If you keep heating a liquid, eventually it will melt to form a gas. And it can go backwards as well. By taking the heat away from a gas, you can cool it until it condenses to be a liquid. And similarly, if you cool down a liquid by taking its heat, it can freeze to form a solid. So let's think about why the temperature doesn't always increase when you heat an object. So to do that, we're going to look at one object and follow it as we heat it from a solid and keep applying heat to it. So we're going to start with a block of ice. Now I've chosen ice just because it's kind of intuitive. You can think of a block of ice easily enough, but remember this could be any solid we could choose. So what happens as you start to heat the solid? So we're going to graph it. We have temperature in degrees Celsius on the y-axis and the energy supplied in joules on the x-axis. So first off, as we heat it, the temperature starts to increase, which is pretty much what we'd expect. And then if we keep heating it, it'll increase a bit more. We keep heating it, its temperature will again keep increasing. So far, it's pretty much what we expected. Except there will reach a point where when you keep applying heat, the temperature no longer goes up. It kind of goes flat for a while. So even though you're applying more and more heat, the temperature has stopped increasing. So what's happening here? Well, what's actually happening is that heat energy is now going in to separating the particles in the solid. There's forces of attraction trying to keep them together, but the heat energy will now be able to give them enough energy to escape from those forces and to separate to form a liquid. That amount of heat, that temperature at which that happens is called the melting point. Here's a little diagram kind of representing what's happening. You've got the solid particles on the left. In a rigid formation, they're vibrating. And you keep applying heat, they can move around a bit more, moving but still kind of close to each other. Okay, and the name for this is the latent heat of fusion, because the particles are fusing together if they're going from a liquid to a solid. So let's keep applying heat. So again, now the temperature starts to increase again because you've now got a liquid. And you can keep applying heat and keep applying heat, and the temperature will keep increasing. But you've probably predicted what's going to happen. It's going to level off again. When you reach a certain temperature for whatever material you're talking about, it will level off again when it's turning from a liquid into a gas. And again, the energy is now needed to overcome those forces of attraction that want to keep the particles together as a liquid so that they can go on to become a gas. A quick note about this diagram: even though it looks like there's less particles in the gas, that's just to show that particles in the gas are more spread out. None of the particles here have been destroyed. No particles were hurt in the making of this video. It's just that they're now separated so much that we have to show that in the diagram. So the heat that we put in to melting a solid was called the latent heat of fusion. Latent just means hidden, so it's hidden heat, because even though we're giving heat to the thing, the temperature hasn't increased. Now we call it fusion. Might be a bit confusing because we use an example of ice melting because it works in both directions. So we call it fusion when a liquid combines together to form a solid. Not to be confused with nuclear fusion, totally different animal, but fusion is just when liquid particles come together to form a solid. And similarly, the heat energy that needs to be applied to turn a liquid to a vapor is called the latent heat of vaporization. For a particular object, the latent heat is the amount of heat energy needed to change the state of that object without causing a change in its temperature. And the System International Unit for latent heat is simply the joule, because it's just associated with that one object. But if you, just like dealing with heat capacity, like we've been talking about before, knowing the latent heat of an object, a single thing, isn't that useful. But knowing the latent heat of certain materials is. So even I don't really care what the latent heat of this chair is, for example. On the other hand, I might be more interested in what is the specific latent heat of fusion or vaporization is for the materials that make up the chair, for like if it's made from a particular metal. So again, just like when we were dealing with um, heat capacity versus specific heat capacity, we want to use the specific latent heat for a material, which is the amount of heat energy needed to change the state of 1 kilo of that substance without causing a change in its temperature. So therefore, the unit for this is going to be joules per kilo, and it's going to only apply to that particular material. The main formula we're going to be using today to quantify the amount of heat energy needed to change something from a liquid to a gas, or a gas to a liquid, or a solid to a liquid is this one here. The energy, which again is represented by Q, like before, is equal to the mass of material, which is little m, always going to be in kilos as per normal, multiplied by this L is now the specific latent heat of that material. So if we're trying to find out how much energy is needed to change a certain amount of material from a liquid to a solid, or a solid to a gas, it's going to be the mass of that material times the specific latent heat, which will give us our answer in joules, which we're going to have a look at some example calculations now. Okay, even before we do so, it's well worth having a look at the worked examples in your textbook before we kind of tackle some of the questions. But we're going to have a look at a few now and see how we go.